All right, geometry, welcome to 8.6 and 13.3. I hope you've been nice to the substitute so far. Anyway, 8.6 and 13.3. 13.3 is a continuation, of course, of 13.2, which was the stuff on slope. I probably should have done this on the same day we talked about tangent because and slope, because this has everything to do with slope. All right, so I actually did this in the notes, so I'm going to do it this way here too. Did I talk about 13.3 first before I talk about 8.6? 13.3 is about how to tell when lines are parallel or perpendicular with slope. Slopes will indicate parallel lines if two lines have the same slope, which I don't think is that big of a surprise. You probably dealt with that in algebra. The more interesting one here is when you have slopes that indicate perpendicular lines. We'll get slopes that indicate perpendicular lines if we have slopes, not because it wouldn't be equal anymore. They're going to have to do this. They're slopes that have this negative reciprocal relationship, like this one with this one. The way they say that in the book is that when you multiply two perpendicular slopes, they multiply and make -1. If I took this slope over here, which happens to be 1.25, and multiply it by -0.8, that would give me exactly -1. And that's the theorem about perpendicular slopes. To illustrate that a bit, I take a right triangle, which of course could be formed by taking any 2 points on any random line and building the coordinate grid street lines north, south, east, west on it, like we always did when we were doing slope and distance and stuff. So the rise and the run on this particular line happens to be a 15:12 ratio, which I would get the same ratio for any 2 points on this line. It would be 15 parts to 12 parts. Give me a slope of 15/12, or 5/4, which has to be 1 1/4, which is a nice number. Now if I took that whole triangle, and I'm going to try something new here. Take that whole triangle and I just rotated it 90 degrees. So it looked like that. I rotate this thing 90 degrees, so you see how the point B goes from here down to here, and the point C goes from there up to here. I moved A a little bit too, so I could kind of show you some of the room in between here. But if you just take this line, or this triangle built on this line, and think about rotating it 90 degrees, I made that a 90-degree rotation. And technically, you know what? I went clockwise, so I guess that's a negative 90-degree rotation. The point is, it's a 90-degree rotation. I did that so that whatever direction this was going, when I rotate it 90 degrees, it's going to be going 90 degrees away from that. So if I extend that hypotenuse and extend this hypotenuse, notice I'm doing this so that I'm sure this is 90 degrees. Okay, so what is the slope of this going to be? Because remember, we're trying to compare this slope to this slope. Well, when I rotated that thing 90 degrees, this rise, this segment from A to B, became this segment down here, A prime to B prime. So that's the 15. This thing that was the 12 got rotated from AC to A prime C prime. So it sort of got flipped upwards here, and now it's the rise. It's 12. So the rise and the run essentially have changed positions when I've done that. So the rise over run is going to now look sort of like a reciprocal of this, because rise and run used to be over 15/12. Now rise over run is 12/15. The other difference here is that this one, of course, is going downhill. This one was going uphill, so it was a positive slope. This one's going downhill, so it's going to be a negative slope. Or if you think about this, the rise here is technically, I should probably be a little more careful about that. That's like a -12, because it's 12 down, and the run is a positive 15. So that's why we see that slope. And if you want to check this, 1.25 times -0.8 equals -1. So in fact, yes, according to the theorem, also, these are perpendicular lines. All right, to show you another example here of perpendicular slope. So you have any old random points on the number line, and it's, or sorry, on the coordinate plane, and it's saying let's construct some perpendiculars here. So if I know I have a point here at, well, this looks like it might be 1, 4. And I have another point here that's supposed to be down here at, I'll say 5, 1. I'll say, okay, I want something to travel through here and be perpendicular to that. Or if I was given something here, is it perpendicular? Well, we need to find out the slope of this line first. What's the slope of that? Well, that's going to be rise over run. And the rise over run here, we've done this plenty by now when we had to find distances or slope. So it looks like it's going to be a downhill slope. The amount downhill, I'm going from a height of 4 here to a height of 1. So this height is 4. This height is 1. So the vertical rise here is like saying a rise of -3. And the horizontal run here, I'm going from a x-coordinate of 1 to an x-coordinate of 5. So that x-coordinate run is 4. So I'll say the slope of this line, of course they always use m for some reason, the slope of that line is rise over run. So slope of this is -3/4. Great. What I was just saying in the previous document there was that if I have a slope of -3/4, if that's to be perpendicular to another slope, that other slope has to be the opposite reciprocal of 3/4. So I take the 3/4 and I turn it upside down. That's a really bad fraction bar. Okay. 4/3, and I change it from from negative now to positive. So anything that's supposed to be perpendicular along here, well, let's say it's supposed to go through here. Why not? I said at the beginning, I'm just looking for anything that's perpendicular. If this is actually perpendicular, I know that the slope on this line has to equal 4/3, if that is supposed to be perpendicular. So we could locate some point on here. As long as its rise over its run is 4/3, that ought to work. So, well, if I went up here by 4, I could be able to go out here by 3, and that should work, right? So this x-coordinate should be on this line. Or sorry, this coordinate here should be on the line. Rise would have to be 4, and run would have to be 3. This isn't a great picture, but it's not bad. And you see what can be kind of confusing about this is you get so excited about 4/3, you think, oh, good, the point 4,3, that should be on there. Well, no, be careful. Remember, this is a y measurement on top because this is rise, and this is a run measurement on the bottom. So it's the change in y over the change in x. So when you're trying to read coordinates out of your slopes, you gotta be a little bit careful if we're connecting to 0, 0. And 0, 0 I picked conveniently because it's really easy to subtract and figure out the rise and run if we're talking about 0, 0. Anyway, my point is, slope of -3/4 is perpendicular to slope of 4/3. Okay, so now for the real interesting stuff about today, which has to do with sine and cosine. We talked about tangent last time. I put tangent here to remind you what that meant. Tangent was once you're talking about a right triangle and you decide on which angle you're trying to find the tangent of, tangent is defined to be the opposite side divided by the adjacent side, which here will be this side, the side opposite B. That's opposite B, to that ratio of that side divided by the side next to B. And we're talking about legs here. It's opposite leg divided by adjacent leg. Hypotenuse has no business being any part of tangent. Well, there's, with these 3 different sides here, there's actually 3 different ratios we could describe relative to angle B. One involves opposite and adjacent. There's another one that involves opposite and hypotenuse. And there's another one that involves adjacent and hypotenuse. Those 3 different ratios have 3 different names. Tangent we already talked about, but here comes sine and cosine. Sine is defined to be the one that's this opposite number, sort of like the rise, divided by the hypotenuse. So kind of like what percentage is hypotenuse, opposite of hypotenuse? That would be the sine. And sort of what percentage is the adjacent leg going to be of the hypotenuse? That's the cosine. And all 3 of those ratios are different most of the time for sine, cosine, and tangent. But here I'm finding the sine and the cosine and the tangent of angle B. Angle B, it turns out, this is from a sketchpad document, angle B happens to have a ratio, or happens to have a degree measure of 58 degrees. The tangent of 58 degrees is to tell us that the opposite over the adjacent, like this opposite length, is about 1.61 times larger than the adjacent leg. The sine is telling us that this opposite leg in any right triangle that has a 58-degree angle in it, that this opposite leg will be 0.85, or like 85% of the hypotenuse. That's what it means at 58 degrees. And that the cosine, this part here, is a little bigger than half of the hypotenuse. And that's how that works. Here's that original document then in the sketchpad version. I can kind of show you how it works if we play around with it a little bit. So if I make that angle really small, now my angle at B here is like 15 degrees. At 15 degrees, if we're talking about sine or cosine, well, sine, I have this little tiny side right here, and its ratio to this piece, to the hypotenuse, the sine is on a little tiny piece of the hypotenuse. It's about 26% of the hypotenuse. Now, at these small angles, the adjacent leg is starting to get really close to the size of the hypotenuse. I make that really small. The hypotenuse and the adjacent leg to angle B start to both get to be pretty much the same. So right now it's 98%, at 11 degrees even. This thing is 98% of the length of that. Now the sine, of course, is a lot smaller. It's only 20%. And as we move on up, remember we kind of had some special stuff going on around 45 degrees. That's when the tangent was 1, because these 2 sides were the same. Opposite divided by adjacent was 1. Around that point, of course, then the opposite over hypotenuse is going to equal just about the same thing as the adjacent over the hypotenuse, because opposite and adjacent are almost equal. Divide them by the same hypotenuse, you get almost the same ratio. And if I was exactly up at 45 degrees here, which I might be able to do, you would see they would actually be the same. but I can't exactly get there. Believe me, they are. We talk about that a lot in FST. In fact, we just did that. And if this starts to get really huge, if B is a very large angle, or the largest B can get is around, is still to be less than 90 in our study of trig here. Whoops, accidentally right-clicked. Right now, B is 81 degrees, and even by 81 degrees, the sine is starting to get very large. Sine here, this is now 99% of the hypotenuse by 81 degrees. The cosine here tells us about the relationship between this one and the hypotenuse, and that's pretty small. It's only 15% of the hypotenuse. And by now, the tangent's getting very large, too. This is 6.5 times longer than that. So you notice, just looking at these, that the tangent, we talked about this last time, tangent can kind of be anything. Tangent can be very small. It could be like, 0.29, or it could be like this, is like 6.5, or even larger if this angle gets bigger. But since the hypotenuse is always the longest side of the triangle, that kind of limits what these values are going to be, because they're always being divided, they're always being compared to the hypotenuse. And the hypotenuse is always longer. So since the hypotenuse is always longer than opposite, and the hypotenuse is always longer than the adjacent, we always get these fractions where the big number's on the bottom. You notice in both these. So the answers for sine and cosine are always going to be numbers that are less than 1. So here's some wacky values. I can really get this sine to be really small here. So here sine is like 9%, but cosine's supposed to be less than 1. It's just being rounded. Trust me on that. See, it goes down really fast. Because cosine can never be 1, right? Because this adjacent leg down here can never be exactly the same length as the hypotenuse. We would never right triangle. Big angle is supposed to be opposite biggest side. A squared plus B squared equals C squared after all. And B squared was something, so A squared has to be less than C squared. Or adjacent has to be less than hypotenuse. All right, so right now it's about 98% there, but it really can't get to be 1. That's a rounding error. Or they rounded it up. It's probably 0.998 or something. And then, yeah, on down. As I keep going way up here, and as this angle for B gets really large, can I just jump that off the screen? I probably could, but let's do this. Again, sine's never going to get to be 1, because this is never going to get to be all of the same length as this. Cosine can get very small, but it's never going to go negative in the right triangle. And this is never going to get to be 1. So cosine and sine answers are always between 0 and 1. So to try to remember these three relationships, that sine equals opposite over hypotenuse, and cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. People for a long time have been using this little device here called SOHCAHTOA to try to remember that, and it's been used in lots of places. So I did not make this up. I do not take credit. All right, if this is the angle we're talking about, I'm going to keep calling it B, because it was triangle ABC in the original triangle and in the notes and stuff. So we'll just say B, because if we talk about a different angle, then these names change places. Remember, we talked about that in the days we were talking about tangent. If I'm saying, okay, we're going to be talking about the sine of B or the cosine of B or the tangent of B, I mean this angle here. And once I say I'm talking about this angle, that makes this side the opposite side and this side the adjacent side. If I was talking about this angle up here, those names would trade places, because now if this is the designated angle, this would be the opposite side, and this would be the adjacent side, and that's totally different, so you have to be careful. The names of opposite and adjacent only come after you know which angle you're talking about. However, this is always the hypotenuse, no matter what. Okay, so SOHCAHTOA. There's a long joke about how this is the name of a Native American Indian chief, and he's got these 3 daughters, and then there's a hippopotamus involved to help you remember. It's really funny, but I'm not going to do as good a job telling you here. So if you want to look that up, I'm sure you can find it online. All right, SOHCAHTOA comes from this. So you write the so this way. See the SOH? You write the ka this way, ka. And really, this as silly as this sounds, this is like one of the best ways to remember that. And toa looks like this, SOHCAHTOA. And it basically means that the sine is the opposite over the hypotenuse, that the cosine is the adjacent over the hypotenuse, and that the tangent is the of B is the opposite over adjacent, which is the one we already did. Okay, I'm gonna have to catch you later and do some problems in part 2.